Okay, now that we are introduced to derivatives of vector valued functions, then the next step in calculus is naturally to figure out how to differentiate sums and scalar multiples and so on, some rules for differentiation. So suppose u of t and v of t are continuously differentiable. Functions of t, okay, as functions of t on some interval, if you like. Then here are some of the rules for differentiation. The derivative with respect to t of the sum of u plus v is the sum of the derivatives, which means you differentiate each component vector like we saw in the last video. If you take this derivative of a scalar multiple of u, of a vector value function, then you just leave the scalar and differentiate the vector valued function. So here alpha is a real number, okay? What about if we start with a little more complicated things? What about if we start with a scalar value function times u of t? Okay, so this is this for each value of t, this gives me a scalar. So this is a function of t, a scalar function of t times a vector value function. How do I differentiate that? Well, it turns out it's probably what you would guess. You differentiate the scalar value function and you multiply times the vector value function, plus you take the scalar value function times the derivative of the vector value function. Now, I'll show you that one, the rule later, the proof of that one later. But for right now, I'm just going to finish stating the rules. Suppose you want to take the derivative of the dot product of these two vector value functions, u and v. Okay, so remember that the dot product is going to give me a scalar. All right, so how do I get what I need to get on the right-hand side better also give me a scalar? And it is, again, I think exactly what you would guess. If you were guessing what the answer is, you differentiate the first dotted with the second, plus the derivative of the second dotted with the first. And since the dot product's commutative, it doesn't matter which order you write that in, okay? What about the derivative of the cross product? Now remember, when you take the cross product of two vectors, okay, maybe I should write the answer down here. When you take the cross product of two vectors, you get another vector. So what I get on the right-hand side better also be a vector. And if you were guessing, I think you would probably guess the answer. So you take the derivative of the first cross the second plus the first cross the derivative of the second. Okay, but unlike above, where it doesn't matter which order you write this in, since the cross product is not commutative, it very much matters that you write it exactly in this order. And then finally, the chain rule, basically. That says that the derivative with respect to t of the vector function u evaluated at f of t. Okay, so in other words, you evaluate each one of the component functions of u at f of t. Okay, so this is equal to u prime at f of t times f prime of t, which again is what I believe you would guess if you were guessing what the answer was based on knowing calculus 1 only. Whoops, I left that where you couldn't quite see it. Okay. So the proof of 1 and 2 are very, very easy. let's see why 3 is true. So let's look at the proof of 3. Okay. So you want to take the derivative with respect to t of f of t times u of t. All right, so let's suppose that u has components u1, u2, u3. So this means taking the derivative with respect to t of the vector f of t times u1 of t, f of t times u2 of t, comma, f of t times u3 of t. Okay, so those are all components in there, okay? And so how do you take the derivative here? Well, we saw in the last video that the way you do that is you take the derivatives inside. So this is going to be d by dt of fu1, d by dt of fu2, d by dt of fu3, that vector. All right, and so let's be careful. What is that? By the product rule, now these are really all scalar functions. So by the product rule of calculus 1, this right-hand side is equal to f prime u1 plus f, I should have written of t, but since we have so much to write and it's going to be hard to fit, I will just write it like this, plus f u1 prime. Then I'll have f prime u2 plus f u2 prime plus f prime u3 plus fu3 prime, square bracket. Okay, and so notice that I can group these into two separate vectors. I can group that into everything that involves an f prime in one and factor out the f prime. So that will be f prime times, here's a term involving f prime here and here. So that will be f prime times u1, u2, u3, plus the term that involves f, which is this one, and this one. So, and if I factor out the common factor of f, that will be f times u1 prime, second component, u2 prime, third component, u3 prime. And then notice that is f prime of t times the vector u of t plus f of t times the vector u prime of t. Okay, so that's all you had to show. And the other ones are pretty easy to do too, especially the dot product and the cross product. The chain rule is a little trickier, but you can read the proof in the book if you're interested in that. But I'm not going to do it here. Okay, but I do want to do an example, an interesting example. So in this example, suppose we look at a vector of constant length. So this is a vector valued function of one parameter whose length is equal to a constant. Okay. Then the tangent vector to that curve, r prime of t, is orthogonal to the vector valued function r of t. Okay, and that's always true. Let's see why that's true. Well, let's see. The length of r squared is equal to what? By definition of the dot product, that is r of t dotted with r of t. Okay, that's a definition of the the dot product and its relationship to length. On the other hand, this is equal to c squared. So so let me differentiate with respect to t, c squared, which of course is going to give me 0, has to be equal to the derivative with respect to t of the length of r of t squared which is equal to the derivative with respect to t of r of t dotted with r of t. So on the one hand, this left-hand side, the derivative of a constant is 0. By the rules of differentiation, we learned this is r prime dotted with r plus r dotted with r prime. But the dot product is commutative, so this is 2 times r dot prime of t dotted with r of t is equal to 0. So therefore, r prime dotted with r is equal to 0, and r prime, whoops, can't see it here. So r prime of t is orthogonal to r of t. I like to use the old high school notation for orthogonal. It saves some writing. That's less important here than on the blackboard, but or whiteboard at the university, but it's still a handy notation to have. Okay, so there you have differentiation rules for vector value functions of a single parameter.